All right, so this is the part 2 to section 1.2 video. This is just going to continue where I left off in the last video. I discussed the concepts. This video is meant to just go over examples. There might be some concepts I'll go over, but I'll be a lot more brief in this video. So at this stage, we should already know you can get a limit numerically, graphically, and analytically. This section 1.2 deals with finding a numerical approach and graphical approach. And you should all be familiar already with what a limit is based on the last video. And so I'm going to jump into these two examples. So I'm going to find the limit numerically. Now, if I did the first one, so I usually make a table. Let's see, so I usually give I'll do columns. First column's x, and then second column's f of x. And then you want to pick values that are close to 4. And I usually go with 4 values, or 4 values total, 2 of them being to the left of 4, and 2 of them being to the right of 4. It's really up to you. So let's see, I have 3.99, that's one of the values, 3.999, and then we have 4, which we're trying to find. So I'll put a question mark there, and then 4.001, and then 4.01. So these are 4 values I picked, 2 of them to the left of 4, 2 of them to the right of 4. And all you do is you plug it into the function. So for instance, if I did 3.99, so my function is this x minus 4 over x squared minus 5x plus 4. So it'd be f of 3.99. That's going to be 3.99 minus 4 over 3.99 squared minus 5 times 3.99. And then plus 4. All right, so I would use the calculator to calculate all this. You could put the entire numerator in parentheses and then hit the division sign and then put the entire denominator in parentheses. And what you get when you do this in the calculator, so I'm leaving that up to you to do the calculations. You get to use a calculator in this course. Now, as long as you sort of really what I'm looking for some problem like this is this table. So because that table will justify what your estimation is going to be. This is just an example of finding one of the particular values that goes in the table. After you calculate this, you get 0.33445, and I just stopped there. And then you do the same thing for the next one. You just plug in 3.999 instead, and you'll get this after you plug it in. 0.33344. And then same thing for these last two. You plug them in and see what the output is. This one, I get 0.3322, and then this other one, 0.33. 223. All right, and that's the table. And if you see that the values, as I get closer to 4 from the left side, these values are getting closer and closer to looks like 3 repeating. And as I approach from the right side of 4, these are getting closer to 0.3 repeating. So I'll summarize as, and again, I use X and then the arrow for approaches. So approaches 4 from the left. The f of x values look like they're approaching 0.3 repeating, or 1/3. And then as you approach from the right side, it's the same thing. They're approaching the 0.3 repeating. And you see this is an estimation. I'm just kind of estimating that it is 0.3 repeating based on the pattern. So that's why I use the analytical approach to have a more exact answer, which is going to be the next section. So from the right, that approach is 0.3 repeating. So since they both approach the same value, we can conclude by using the numerical approach that the limit is 0.3 repeating, or 1/3. Okay, so that's going to be the answer. And I'm going to do the same idea just for the other one. I sine of x over x. So again, I make a table, and this time I want it to be getting closer to 0. So I'll make my table. So I have x and then f of x. I'll pick 4 values, 2 of them to the left of 0. Like for instance, I could have negative 0.01. I could have negative 0.001. And then it gets to 0, which that's the question we want to find out. And then 2 to the right of 0, we could have 0.001 and then 0.01. And similar logic, I plug them in just for demonstration if I did negative 0.01. That's going to be equal to sine of negative 0.01 divided by negative 0.01. And yeah, I would use the calculator, make sure it's in radians, and you get this to be, let's see, so it's 0.9, so this 4 nines, so 999, and then 8. All right, so that's the first one. And then do same process. The other ones, I'm just going to go ahead and write what they come out to be. And it looks like they're approaching either 0.9 repeating, or you could say 1. So it's getting closer and closer to 1. Okay, so that's getting closer to 1. And that's getting closer to 1. So I'd write it as x approaches 0 from the left. F of x approaches 1, or I would accept f of x approaches 0.9 repeating, which 0.9 repeating is actually equivalent to 1. Right, so then they both approach the same value from both sides. So approaches the same value from both sides. So we write the answer, limit x goes to 0, sine of x over x, say equals to 1, or equals to 0.9 repeating. Okay, so that's using the numerical approach. These next couple examples are going to be doing the graphical approach. So for the following, and the limit from its graph. And I'll go ahead and provide you with the graph. All right, limit as x goes to 3, and it's 4 minus x. So in this case, our function is 4 minus x. That's going to be a line that intercepts the y-axis at 4. The y-intercepts 4. So as far as what this looks like, we'll use different color. Let's say I did green for the line. So it looks something like this. All right, and the y-intercept is 0, 4. Now, as x approaches 3 from the left side, so I'll use purple. So as I'm getting closer and closer to 3 from the left side, the graph is getting closer and closer to this point. And that point is 3, 1. And now if I approach it from the right side, then the graph is getting closer and closer to that same point. So the limit's going to be 1. It's the y coordinate of that point. So as x approaches 3 from the left, the y coordinates approach the 1. And then same thing for the right, they approach 1. All right, so since they're the same, then the limit is going to be 1. So let me move on. All right, say I give you the function f of x equal to, and it's broken into the following. So 4 minus x, if x is not equal to 2, and then equal to 0, if x is equal to 2. And I'm going to find the limit as x goes to 2. All right, this problem had the same function, 4 minus x. This is called a piecewise function. It's broken into 2 different pieces. So it's going to look similar to the graph I had. The only thing is when I get to 2, so normally I would have this line, and this might be better if I wrote it like that. So normally I would have that line. Now because this is a piecewise function, I need to exclude the point on the line when x is 2 because x can't be 2. So exclude where 2 is, so I'm going to have a hole at that point. And then it tells us for the second piece, this gives us what 2 turns out to be, what its output is. So this gives 2, 0. That's the point right there. So this is a piecewise function. There's a hole in the graph on the line that's provided by 4 minus x when x is 2. And that hole is the point 2, 2. But the point itself is, so it's like you jump and then put the point on the x-axis at 2. So the point is actually defined at 2, 0. All right, so when finding the limit, now if I approach 2 from the right side, so this example is important. So if I approach 2 from the right side, for the x values approaching 2 from the right side, the graph itself is still this line, and it's getting closer and closer to that hole, even though there's this dot where it's defined at. So it's still getting closer to the hole. Now, if I could approach 2 from the left side, the graph itself is still approaching this hole. So even though there's the defined point that's somewhere else, the limit of the graph still is approaching the same value of where the hole is. So as x approaches 2 from the right, because the graph is mainly this entire line minus that hole, the y coordinates that are on the line are approaching the y coordinate of the hole, which is 2. And then same thing for when we approach 2 from the left, the y coordinates are on this line, and for that line they're still approaching the hole, which has a y coordinate of 2. So they're the same value, and so the limit is going to be 2. Even though there's a hole in the graph. So that's important because I have this point, that purple point that's defined, 2, 0. And the y coordinates, so the points that are around that are on this line. And since they're on the line, they get closer and closer to the hole. They don't get closer to the purple point. All right, since we're dealing with this entire just line minus the hole, so that hole itself is actually the limit. So that's kind of a, I think, important example. All right, so another example. Let's say I wanted to limit x goes to 2, and our function is the absolute value of x minus 2 over x minus 2. And I'll go ahead and provide the graph, so what its graph looks like. So it has this portion that goes to the right at 2, and then it jumps down here, we're at -1, and then goes forever to the left at 2. So that's what the graph looks like. Now, if I focus on, well, what's the limit? So if I'm approaching 2 from the right side, my y coordinates jump to this part of the graph, just this line, and they're getting closer and closer to that hole. And that hole has a y coordinate of 1. So that's 2, 1 is the hole. So as the x values get closer to 2 from the right side, the function, the y coordinates, f of x, are getting closer and closer to this hole that's at the top, which has got a y coordinate of 1. Now if I approach 2 from the left side, that's the y coordinates are on this portion of the graph, this bottom line. And that approaches the bottom hole, and that hole has is the point 2, -1. So the y coordinate of that is -1. Notice I have 2 different values if I depending on which direction I'm approaching to. So 2 different values. Not the same, so we would say the limit doesn't exist. So limit X goes to 2, the absolute value of x minus 2 of x minus 2 does not exist. They have to approach the same particular value. So usually I go D and E for doesn't exist. So that was important. That's the case when the limit doesn't exist. If the limit approaches two different values, so if the graph approaches two different values from the left and right side, they have to match up. All right, so this next one, I'll just provide the graph. So let's say there's this vertical asymptote. And that vertical asymptote is at 2. So I use VA for vertical asymptote, and it's x equals 2. Now if I'm going to use green for the graph, and the vertical asymptote describes what behavior of the graph. So if I get closer and closer to 2, this thing's either going to go up to positive infinity or negative infinity. So let's say the graph does this. It goes forever and ever up. And then let's say it jumps down here to this portion, it goes forever down. So the f of x is the green. Let's say I want to know what's the limit as x approaches 2 for this graph. Well, if I get closer to 2 on the right side, the y-coordinates of this are going up forever to positive infinity. It shoots up forever to positive infinity. So as x approaches 2 from the right, the f of x values get infinitely big. They approach positive infinity. Now if I approach 2 from the left side, the y-coordinates are on this portion of the graph, and they're going down forever to negative infinity. Now the point is that they don't approach a finite value. So neither one of these approaches a finite value. So since they don't approach a finite value, then the limit does not exist. So we have limit x goes to 2 of f of x does not exist. So I'll put D and E. And again, this is what happens when you have a vertical asymptote. So your limit has to approach a finite value. I'm going to do one more. Oh, I don't know what just happened there. All right, so all right, so these are my axes, and I'll use green again for the graph. And let's say as I it does something like this, and then I get closer and closer to 0, it does this oscillation pattern, and then levels off like that. And then I want to know what's the limit of f of x as it goes to 0. And let's see this oscillation, the peaks occur at 1 and -1. So if I approach 0 from the right side, your graph's going to be oscillating between 1 and -1. So the y coordinates are going to be sort of getting oscillating between 1 and -1. F of x oscillates between 1 and -1. And same thing for the right side, approaching 0 from the right side. So this thing is oscillating between 1 and -1. The point is that you have this oscillation between two values. It's not a single value. So since it oscillates between two values and not a single value, then the limit doesn't exist in this case either. So I'm saying is not a single value. We'd say the limit doesn't exist. All right, so I've provided 3 cases where the limit doesn't exist. And these rely, so I'm going to summarize. So to summarize, the limit does not exist when you have one of the following. Well, one of them dealt with approaching 2 different values from the left side and right side. So like this one, as I approach 2 from the right, it approached 1, approaching 2 from the left, it approaches -1. So there's 2 different values depending on each side. So you could have as x approaches some value c from the right, and then f of x approaches, I'm just going to call it L1, and as x approaches c from the left, f of x approaches L2, and L1 and L2 are not the same value. All right, so the limit approaches 2 different values, L1 and L2. The second scenario where it didn't exist was this one where I had it as like a vertical asymptote, and the graph just was unbounded, is what it's called, unbounded behavior. It approached positive infinity or negative infinity. So I'm writing unbounded behavior. Meaning that as x approaches c, f of x approaches infinity, or f of x approaches negative infinity. And then the third case where the limit doesn't exist is this oscillation pattern. It doesn't approach one particular value. So I'm going to say it doesn't fixate at one specific value. All right, those are the three cases from the graphs that I drew that you'll run into where the limit doesn't exist. All right, so that's where I'll stop it with this video, and I'll begin the next section, 1.3, the next video.